Okay, everyone. Good afternoon. Good evening. So this morning we did an example, and we saw how to change integrals over a region in the plane. How to change the coordinate system. Okay. So this very much changes how the integral presents. So we're changing typically from the Cartesian coordinate system over to some alternative coordinate system, just general new pair of coordinates s and t there. And the change happens, well, we change all the bits of the integral, meaning the original function f expressed in terms of x and y, you would change that to a representation, the same function, but now expressed in terms of the new variables. The old differentials dx and dy, in their place go ds and dt, and there's an extra factor. And this extra factor takes account of the different ways that changes in the variables affect the area of points covered. And in general, the area element, so in Cartesian coordinates, the area element is dx dy. So that means that when you vary the x and y coordinates, the area of the plane covered by that change is simply dx dy. It's independent of the location in the plane where you are. But for other coordinate systems, such as the polar coordinate system where we saw, the amount of area covered by variations in the coordinates is sensitive to your location. If you're close to the origin, a change in the polar angle induces a small change in area. But if you're far away from the origin, that same change in polar angle theta is now sweeping across a huge region of space if you're far away from the origin. So the presence of the Jacobian factor takes account of that. We saw an example where we tackled this two-dimensional integral, 1 over x squared plus y squared, integrating it over this region R, this shaded annular region between two circles. Okay, and we saw how changing over to the polar coordinate system meant that the integral could be evaluated relatively painlessly once we'd made the change. Okay, once we changed over into the new coordinate system. Now, this is all very well in 2 dimensions. The same thing can be done in higher dimensions. So this coordinate change formula here, expressed here for 2 dimensions, going from the Cartesian coordinate system to a new system s and t, the same thing can be said, that the same generalization happens in any number of dimensions. So doing a multi-integral of a function of n variables over this portion, this sub-region of n-dimensional space, the sub-region R, we can change to a new system of coordinates. So the new system of coordinates is here represented as u1 up through un. We would replace each of the original variables xi by their representation in terms of the new coordinates u1 through un. That's what's represented here, the xi represented as some function of the u1s up to un. And we do that for each of the original variables x1 through xn. We have new differentials, du1, du2, du3, etc., all the way to dun. But to complete the area element in the new system of coordinates, we have, again, the absolute value of the Jacobian of the transformation from the original Cartesian coordinates to the new set of coordinates. So we'd like to do another couple of examples just to get us familiar with working with these things, and just to see how it plays out in 3 dimensions. Okay, so we're going to work through some extra examples here, which aren't in the notes, but we'll set these out here on the page. So here's some 3D examples. Examples. So our first example is we're going to consider subset R, which is a subset of the three-dimensional space R cubed. So R cubed we think of as the x, y, z space. And this region, or this sub-volume, or sub-region of R3 is bounded by z equals 0 xy plane. So it's bounded below by the xy plane at level z equals 0. And the paraboloid defined by rho squared equals 9 minus z, where rho is the projected radius of a point. Okay, so if you have a point in three-dimensional space hovering up here, it has a certain radius r. So if we think of our x, y, and z axes with the origin down at this bottom corner here. So you've got the x-axis running along this edge of the floor and wall, the y-axis running along there, and the z-axis running up the corner wall. Forget about the funny boxing stuff. So some point out here, it has a radius, and that's just the straight line going from the point back to the origin. Rho, the projected radius, is when we take the vertical projection of all space down onto the xy plane on the floor, then that radius line projects down into a line along the xy plane, running from the origin to vertically underneath the point. And that's the projected radius, rho. So you take a vertical projection down onto the xy plane, and this line there is rho, the projected radius. And we are going to be asked to use the projected radius of a point onto the xy plane. And our task here is to evaluate the integral. So it's a triple integral over R, because we're integrating over a portion of three-dimensional space. And we want to integrate the function rho squared dx, dy, dz. Now we need a good sketch of this region, okay? First of all, just so we know what we're thinking about. So here's the x, y, and z axes. The region is bounded on the bottom by the xy plane, and it's bounded by this paraboloid, rho squared equals 9 minus z. So that means this paraboloid has circular cross sections. When we take cross sections of it parallel to the xy plane, okay, then we can view that. We can view the projected radius as the radius of that circular cross section, and it's going to have a 0 radius up at the level z equals 9, because then you're going to have rho squared equals 9 minus 9. And when z is equal to 0, down on the floor, it's going to have a squared radius, rho squared equals 9. So that means it's going to have radius 3. So these points that are 3 on the x and y axes, we're going to have this circle in the bottom, the circle of radius 3 in the bottom plane. And then this paraboloid is just going to come up, and the square of the radius is going to decrease. So we can see this portion of the surface here. So I'll just draw in now the stuff we can see. So you get the idea. It's this kind of like bell-shaped paraboloid. Okay. So rho is the projected radius. So if you cut this paraboloid parallel to the xy plane, it'll have a circular cross-section of radius rho. And the radius goes from a radius of 0 up near the point at the top, down to a radius of 3, because you have rho squared equals 9, down at the z equals 0 level. Sorry?
Please can you explain the shape?
So the shape is just like this, a paraboloid. So it's like a three-dimensional version of a parabola. Okay? It's a shape that has, when you take a cross-section of it parallel to the xy plane, the cross-section is a circle. Okay? Because it's defined in terms of this equation, rho squared equals 9 minus z. So rho is the projected radius. So we're considering points on it that have a projected radius of 9 minus z. Okay? So it's got this various projected radius value at various levels of z. At z equals 0, the square of the radius is 9. So the radius is 3. So where it meets the xy plane on the ground is a circle of radius 3, centered on the origin. And as it comes up, the circles decrease in height until you reach a height of z equals 9. So this level up here is z equals 9. And then you have rho squared equals 9 minus 9, 0. Okay? So it's this kind of bell-shaped paraboloid with circular cross-sections. Okay? Now, what coordinate system is good for describing this? Well, the portion of space is symmetric around the z-axis. Okay, so it's symmetrical around the z-axis. And we've already got this quantity rho, the projected radius, featuring in the description. Okay? So that really suggests, the context suggests using the cylindrical coordinate system. And then we defined this a few weeks ago when we were originally when we originally presented the definition of the Jacobian transformations. So the cylindrical coordinate system measures the location of a point by quoting its projected radius, rho, this distance, the angle that projected radius makes with the positive x-axis, and the z, the normal Cartesian z height of the point. Okay, so the cylindrical coordinate system is this triple rho theta z. Sorry, I'm changing my z's. Keep my z's consistent. Rho theta z. And the linking transformation equations are x is rho cosine theta, y is rho sine theta, and well, z is z. It's the same transformation equation because it's the same coordinate. This z coordinate is just the regular Cartesian z coordinate, and it also features in the cylindrical coordinate system. So in order to carry out the transformation, we're going to need the Jacobian of this transformation. I can't remember if I left it as an exercise for you last time when we first introduced the Jacobians. But I'll show you the calculation again now. It's good to remind ourselves of it. So it's this 3×3 determinant. It's the 3×3 determinant of the partial derivatives. Okay, so there's 9 partial derivatives differentiating one of these variables with respect to one of the new variables. One of x, y, and z with respect to one of the new variables. So in the matrix, the rows are indexed by the old variables, the top variables. And the new variables index the columns. Okay, so you've got the second row is the y row. So this should be x. The last row is the z row. I think I did some of this derivation before. There's no harm to see it again. So this is our 3x3 determinant. The individual entries of it we obtain by taking partial derivatives of the transformation equations. And looking at these, so dx d rho is going to be cosine theta. Dx d theta is going to be minus rho sine theta. Dx dz, well, x doesn't depend on z, so that derivative is 0. dy d rho is sine theta. dy d theta is going to be rho cosine theta. And dy dz is again 0. And dz d rho, dz d theta, well, z is independent of rho and theta, so those two derivatives are 0. And dz dz, well, the derivative of z with respect to z is 1. Okay, so that's what the Jacobian determinant looks like. And we're all used to, since we're in the middle of doing coursework, of simplifying determinants by extracting common factors. You can see that there's a common factor there in the middle column of rho. Rho is also present as a factor of 0, so we can extract out that common factor. So this is rho times cosine theta, sine theta, minus sine theta, 0, 0, 1, 0, 0. And well, this determinant can be immediately expanded along the bottom row, and it will give you cosine squared theta plus sine squared theta. So the value of the Jacobian is rho. So this is going to make an appearance in the new area element, because the new area element is going to be rho d theta dz. So we can now transform the integral, translate the integral from Cartesian coordinates into cylindrical coordinates. Are any questions just about the derivation of the Jacobian? Okay. So returning to the integral now, we'll worry about limits in a moment. So it's a triple integral over R. Well, the function we're integrating is already expressed in terms of the new coordinate system. And then you've got an extra rho for the Jacobian, d rho, d theta, dz. Or you could say absolute value of rho, because that's what the formula calls for, the absolute value of the Jacobian, except rho is by definition a positive quantity. So it's the length of the projected radius. So it only ever is a non-negative quantity. So it doesn't require absolute value signs. Okay, so I think we're ready to start deciding on limits of integration now. So we're integrating rho cubed. You can stick with this original order, d rho, d theta, dz. And now remember, this is a nested set of integrals, one inside the other. We need to, in order to evaluate it, we need to determine the individual limits on each of the variables. So we need to think of this region and think about what the various variables are doing in order to determine these limits. And we work from the outside in, okay, because the z integral is the top level operation here. This quantity is a z integral of stuff. So between what limits of the z variable do we have to integrate in order to capture our volume R, or our region R? Well, we need to integrate from z equals 0 up to z equals 9. Okay? We were told the region is bounded by the xy plane at the bottom, and it extends up. Okay? So we're integrating from z equals 0 to 9. So then this outer z integral, this supplies z values to its contents. Okay? So you imagine a typical z value, which is a typical value between 0 and 9, and that gives you a cross-section of the region. So you're talking about a cross-section, which is this disk, the cross-section of the region. How do we describe that in terms of the theta variable and the rho variable? Well, the whole thing is symmetrical around the z-axis. So one of these cross-sectional disks, when we slice it parallel to the xy plane at a certain z level, we need to consider all polar angles theta. Okay? So it's a disk centered on the z-axis. So we need to go for every angle 0 to 2 pi. And now that theta integral supplies its values of the angle theta to the inner rho integral. Okay, so the z integral at the outside, the theta integral in the middle, they're both supplying values of their variables to the inner integral. So between what limits of the rho variable do we need to integrate to capture the region? Well, you see, by the time we get to the inner integral, we're talking about some kind of disk cross-section which is located at a certain height along the z-axis, and we're considering a certain fixed theta angle. So there's the x-axis, so we're considering a certain angle theta there, kind of. So between what values of the rho variable do we have to integrate in order to finish off describing this cross-section? Well, we need to integrate all the way out along this kind of radius of this circular cross-section, but this is really the projected radius. So we need to integrate from rho for 0 to whatever this maximum value of rho is. Well, that's applied to us because we're talking about the paraboloid defined by this equation. So rho goes up to a maximum value where it meets the boundary of the paraboloid, which is at the value, the square root of 9 minus z. So we're going from 0 to the square root of 9 minus z. Okay. Now, it's hard to replicate it on paper, but you need to remember that kind of process as being very much a dynamic process where you're beginning with the empty integral signs. You're working from the outside in, okay, determining the lower and upper limit for each of the variables so that you fully capture and describe the region that you're integrating. And that's most of the battle. Getting it to this stage, getting it set up to this stage, from there on out, it's just kind of patient integration, really. Okay. So we evaluate these things from the inside out. Okay, you got to evaluate subjects of your inner brackets, and then you work out and apply until you apply the last operation, which is the z integral. Well, a little bit of simplification we could spot is that before we actually go ahead and integrate it, this rho integral, it's completely independent of theta. There's no theta in the function we're integrating. There's no theta in the variables. So the inner rho integral doesn't really care what the value of theta is. It does care what the value of z is. It's not independent of z. Okay, there's no z in the integrand, but there is a z in one of the limits. So the inner rho integral, it certainly depends on z, but it doesn't have any dependence on rho. So using the principle of integration, using the linearity of integration, this integral is really just a fixed constant as far as theta is concerned. So we could simplify it slightly by taking the rho integral outside of the theta integral. It's not really going to change much about what we actually do, but it just helps conceptually to simplify the thing a little bit. So it's now no longer three integrals each inside the next. It's now just two integrals inside an outer z integral. So we kind of simplified the structure a little bit. The theta integral is just 2 pi. So you're integrating d theta from 0 to 2 pi. D theta is the length element. But you're integrating 1 d theta, so it integrates the theta. Evaluated at 2 pi and 0, you get 2 pi. Then integrating rho cubed, of course, you get rho to the power of 4 over 4. And you're evaluating this at 0 and the square root of 9 minus z. This 2 pi can move outside. This quarter should also move outside, really. And evaluating this, well, when you evaluate it at rho equals 0, it's just 0. When you evaluate it at the square root of 9 minus z, okay, that's a value that's going in for rho. It raises to the power of 4, so that's the square of 9 minus z. So really we're talking pi over 2, integral from 0 to 9 of z squared minus 18z plus 81. And that will integrate. So everything's unraveling. Back to numbers. Z cubed over cubed. Z cubed over 3 minus 9z squared plus 81z. Evaluated at 0 and 9. When you, what goes on here? So it's pi over 2. Oh, this is. And that is whatever it is. Simplifies a bit. That's 81 times 9 plus 81. So those cancel out. So it's and 80 can cancel the 3. So it's 3 times 81. 3 times 81, whatever that is, times pi over 2. 243 over pi over 2. Okay. So this is the value of the integral of that function rho squared, square of the projected radius, over that portion of the plane R3, 3 pi. We multiply by. Yeah, you okay on that evaluation? That's 81 times 9. Okay. Let's go on and look at an example involving the spherical coordinate system. That's very important as well. It's kind of the generalization of polar coordinates to 3 dimensions, sometimes called 3-dimensional polar coordinates. So this time we set, we're looking for, find the mass of a spherical body of radius A. Well, so sorry, word sphere just refers to the shell, but I mean the sphere and everything in it. So the bowl-shaped region, a radius A, some radius, but it's whose density is inversely proportional to the square of the radial distance. I.e., the density d of this material, of this body, at a certain point x, y, z, is proportional to the inversely proportional. So the square of the radius, that's this quantity x squared plus y squared plus z squared, and it's proportional. So there's some constant of proportionality k, and we have the reciprocal of the square of the radius, x squared plus y squared plus z squared. So this mass m is the triple integral over the sphere of radius a of this quantity k over x squared plus y squared plus z squared times the volume element. And the volume element in Cartesian coordinates is dx, dy, dz. If you're at a point in space, you vary your x, y, and z coordinates, the volume that you describe is the volume of a rectangular box. The volume of a rectangular box is the width by the length by the height. Now this clearly calls for the use of spherical coordinates. Why does it clearly call for the use of spherical coordinates? Well, the region we're integrating over is a ball, is a sphere, and the function we're integrating involves the radius. So all of these things will be easier to describe if we use spherical coordinates instead of Cartesian coordinates. Now, let's remind ourselves of what the spherical coordinates looks like. There's the three-dimensional Cartesian coordinates. A point out here, hovering out here in the middle of the room. There's the origin down there in the bottom corner. So the spherical coordinates are r, theta, phi. R is the length of the radius. Phi is the angle that the radius makes with the z-axis. Like that. And theta, when you project the point vertically downwards onto the xy plane, theta is the so-called polar angle there. The angle that the radius makes with the x-axis. The projected radius makes with the x-axis. Now there's a few triangles here. There's the vertical triangle with r as its hypotenuse. There's this triangle in the xy plane with the projected radius as its hypotenuse. We explained this when we met this before, but when you examine those two rectangles, you find that the transformation equations are z is r cosine phi. That comes from analyzing this vertical triangle, because this top angle here is phi as well, it's the angle opposite to this one. And the x and y coordinates involve the quantity rho sine of phi. That's the length of the projected radius, sorry, r sine phi. That's the length of the projected radius. Y is r sine phi sine, see I'm writing them out in opposite order. Sine theta, and x is r sine phi, that's the length of the projected radius, cosine theta. So those are the transformation equations. Now I don't think I did show you the evaluation of the Jacobian for spherical polar coordinates. It's maybe worth looking at that. It's helpful, I think, for factorizing determinants as well, so it might help you. We're still doing that question of Stevens. So the Jacobian is dx yz dr theta phi. So the same definition as before. Dx dr, dx d theta, dx d phi. We've got a y rho, dy dr, dy d theta, dy d phi. And you got a z rho, dz dr, keep changing my z, sorry, dz d theta, dz d phi. So it's that 3x3 determinant. And each of the 9 entries comes from taking the partial derivative of the appropriate equation with respect to the appropriate variable. So the xdr is sine phi cosine theta. Dx d theta is minus r sine phi sine theta. Dx d phi is r cosine phi cosine theta. Dy dr is sine phi sine theta. Dy d theta is r sine phi cosine theta. And dy d phi is r cosine phi sine theta. The z variable dz dr is cosine phi. Dz d theta is 0 because there aren't any thetas in z. And dz d phi is minus r sine phi. Okay, so you get a intimidating looking 3x3 determinant with 3 variables and sines and cosines of 2 of the variables. Okay? We do not want to just go ahead and expand it out. Instead, we want to look to do whatever factorization we can before we encounter the however many individual terms you get if you expand the 3x3 determinant. So, common factors. Well, there's an r common factor in the second column. There's an r common factor in the third column, so we can take r squared out. And in fact, there's also a common factor of sine phi in the second column as well. So in total, we can take out r sine phi out of the second column and take out an extra r out of the third column. So in total, we can take out r squared sine phi out of all of that. first column remains unchanged. The second column gets factorized. Minus sine theta, cosine theta, still 0. And we've taken r out of the third one. Cosine phi, cosine theta, cosine phi, sine theta, minus sine phi. And there aren't any other common factors remaining. We've taken out all the ones at the right. So I guess now we have to go for expanding out the determinant. You should either expand it down the second column or along the third row, because they contain a 0. And so we will not need to work out the cofactor associated to that position. So we're only going to multiply it by 0, so we don't need to work it out. So let's go expand it along the third row. That's 5, sorry. So we get cosine phi into this top right 2 by 2 determinant, which is minus sine theta, cosine phi, cosine theta, cosine phi, sine theta, and minus whatever that is, 0 times the 2 by 2 determinant, but it's going to be 0, and then plus minus sine theta, sorry, minus sine phi times this top left 2 by 2 determinant. So sine phi, cosine theta, minus sine theta, sine phi, sine theta, cosine theta. Now in these 2 by 2 determinants that come out, we do see common factors. We see a common factor of cosine phi there in the second column, so that can be factored out. But that's interestingly going to give you cosine squared phi. There's a sine phi factor there in that first column. Well, that can be factored out to match with this one, which will turn that into sine squared of phi. So you get cosine squared phi minus sine squared phi. Into the 2 by 2 determinant, which is, I'll just minus sine theta, cosine theta, sine theta, minus sine squared phi, cosine theta minus sine theta, cosine theta. So I'm just writing C's and S's for sine and cosine. But that's nice because when you do these 2 by 2 determinants, we get minus sine squared minus cosine squared, which is minus 1. We do this one, cosine squared minus sine squared is plus 1. So you get a minus 1 from here, plus 1 from that one. So we got minus sine squared phi minus cosine squared phi. That's minus 1. So the whole big square bracket comes out as minus 1. So the Jacobian is minus r squared sine phi. Okay? And that's the missing, that's the last thing we need in order to do the translation of the integral. So this mass of this sphere, which is varying density, remember, inversely proportional to the square of the radius. So it's getting very, very dense at the center. Points near the center of small, tiny radius. So when you invert that, it's going to be a huge number. So potentially infinite density right at the origin. So the function we're integrating is k over r squared. So we're changing to the spherical polar coordinates. So the 1 over x squared plus y squared plus z squared is now 1 over r squared. Taking the absolute value of the Jacobian minus r squared sine phi, and then dr, d theta, dz. Now, how do you describe the sphere in terms of the polar coordinates? There's our polar coordinates again. Oh, sorry, what's that dz? Not dz, d phi. Well, how can you describe a sphere? Well, we can go from 0 to pi on the phi angle. So that takes us from a radius line pointing vertically up, and it's going to sweep it down to a radius line pointing vertically down. So that gives us a kind of a slice through space of this plane from vertically up to vertically down. Stop doing that actually. The theta angle, well, this part we need to rotate all the way around the z-axis to trace out the sphere. We're going to go that from 0 to 2 pi. And the radius, well, the radius, we want to integrate through the spherical bodies. We're going to integrate that from a radius of 0 out to the radius of the sphere, which was set at the start to just be some radius a. So these limits on the variable going from phi pointing vertically up all the way to pointing vertically down, that traces out this kind of sheet extending out across half of space away from the z-axis. We sweep that all the way around the z-axis, and then we only consider radiuses between 0 and a. So that describes the sphere. So from this point, we can integrate. But from this point on, it's just regular old familiar integration. And the answer you'll get, you can check you're working, is 4 pi ak. So although the thing does have unbounded density as you get towards the center, as the inverse of the square of the radius is approaching infinity as you get to the center of the sphere, nevertheless the thing does have a finite mass of 4 pi 8 times k. Okay. Okay, that takes us right up to the end. We'll be doing the final section on this on Green's theorem next week. Final section in this multivariable calculus.